Thank you very much for the invitation. For my first time here in Grenoble, which is very, very nice. Okay, so I gave a title a little generic because I didn't at the beginning know exactly what to talk about. I decided to talk about some non-local functionals which have been considered quite a lot in recent years. In particular, I want to pose some simple questions, review some known answers, and pose some simple questions about the shape of minimizers for a relatively simple non-local energy. So the energy I'm going to consider is, so given it's just a double it's just the energy. Well, to start with, the energy we'll consider is just a double integral. So it's an interaction between particles in a set of a suitable kernel, interaction kernel. Let me also put a plus or minus in front, just because, of course, the behavior is quite different of minimizers. We change this. And so that will be an interaction kernel between points on a set E. And typically, the problem will be coupled with a volume constraint on a set, and I will assume now I don't want to make the more general possible energy, so I will assume something on this kernel, and typically it depends only on the distance between 2 points, so it's a symmetric isotropic kernel, and it's decreasing. It's decreasing, and also in order to be able to give a meaning to this, I will also assume it's in L1 lock. So it's integrable, let's say. Let me write a little bit briefly like that, L1 lock. So typical examples of this kernel. So in some sense, it's if there is a plus here, one has to think this as a repulsive interaction between points, which want to go far one from the other. And if there is a minus, it's rather an attractive interaction between points of the set E. Okay, so typical example is the Coulomb kernel or the gravitational kernel, which is just, so examples are the Coulomb, which means that K, okay, then it depends, up to constant is minus modulus of X. So what is in 2D, it's log of X, and in general, there are constants here, but it's not important. And in general, it's modulus of X to the n minus 2 in dimension. And sometimes one can consider, that's a typical example where, for example, if there is a minus, one thinks at E as something which has a gravitational attraction, so wants to come together. On the other hand, if there is a plus, one can think of something which is charged, and so the charge want to spread, so it's repulsive. Other kernels which have been considered in the literature, in fact, are a slight generalization of this, which are the Ritz kernel, which is simply 1 over x to some power alpha, and I require the power alpha to be less than the dimension in order to be able to give a meaning to this. So an integrability condition. They somewhat behave in a similar way, so sometimes many results can be done for both. So considering, so first of all, for this type, there is an, okay, before stating a result, there is an important tool in this type of problems, which is the Ritz inequality. And the Ritz inequality, which says that if I have an interaction, let's say, instead of taking here the characteristic function of a set, so integrating on a set, I integrate on the wall of Rn. But I take 2 functions, f, g, and then I have k, g of y. And so in particular, this reduces to my energy when f equal g equal to the characteristic of E. And this in general is less than or equal then the symmetrized, so K, it's already symmetric, this kernel here, because I assume the kernel depending only on the distance. And if I symmetrize the functions, do the Schwarz symmetrization, so I rearrange by having the Schwarz symmetrization on each level set, so I make the function rotational invariant and decreasing, I increase this energy. Here, these functions are assumed to be positive, okay? I don't state all the, and okay, so that's an important inequality, which, for example, gives a well-known, immediately a well-known result, which says that if I minimize this energy in the attractive case, and I'm mostly interested in the attractive situation in this talk, if I minimize this energy with a quite general kernel, so decreasing is enough, I get a ball. So the best configuration, if I am in a sort of gravitation, so it's well known. So it's a corollary, sort of immediate corollary of this. So if I minimize minus integral between the sets which are given volume, then by rearranging the function Q of E, using this inequality, rearranges the function Q of E, it's convenient to take a ball, which is a rearranged. And so then the minimum equal the ball of, let me say, the ball of volume M is the minimizer. Unique minimizer, okay, that's well known in fact. Now, first of all, what I want to do is to study this type of problems when I have not only one set, so one phase, but two phases attracting each other. Before going into this, I want just to mention that also the repulsive case, so the case where you put a plus here, has been recently studied quite a bit. And so maybe I just review quickly what has been done in the, not in the attractive, but in the repulsive case where you have a plus here. So in the repulsive case, so typically, for example, if you take Coulomb repulsion, there is not a minimizer because the functional is positive, and it's convenient to spread the charges out to infinity. And so this changes the type of problem with respect to, so in order to be able to get a minimizer, you have to had some extra constraint apart from the volume, and or some extra term. And for example, in the repulsive case, a functional which has been studied, a problem which has been studied recently, it's a problem where you add a perimeter term in order to avoid charges to. You can do many things somehow. You have to avoid the spreading of charges. One way is to add a perimeter term, and that's important because it comes out from some models. I will tell you maybe some other way could just change the potential and make it attractive at large distances. So repulsive at short, attractive at large. That's another sort of two ways to have a non-trivial minimizer. So this has been studied quite a bit because it's a model, it's related to some simple model for the atomic nuclei where you have something, where you have something which is positively charged, for example. And also it comes out in some models, a little different in some models of dibloco polymer. So now here the problem is more complicated than this one, which is very simple, because the existence or not of a minimizer depends, in fact, on this. So let's, for example, consider the simple case of the Coulomb repulsion. So something which is, I consider the perimeter plus a repulsive charge inside. So it's Coulomb repulsion, for example, in 3D, which is a physically relevant case, would be this functional here. And now here, of course, the problem is a little different because there is a competition between an attractive term, let's say the perimeter, which wants you to be a ball by isoperimetric inequality, and something repulsive. The two things here, they do not scale the same. So if we multiply the sets, the guy here scales like, I have twice a volume and something at the denominator. This scales like 2n minus 1. If I multiply, instead of e, I take lambda e. This scales like 2n coming from here, -1, and this case like n-1. And so this wins somehow for small sets. This is much bigger than the other one for small volumes, and this one will be bigger for large volumes. So the behavior here depends very much on the volume. And there are some results. Let me just quote. So there are several results. The first results I'm quoting here, it's maybe from by Knupfer and Muratov, and then there are also results by people even here, Millot, Maggi, Figaldi, many other, Cicalese, Spadago, on variants on this part. So it's been quite studied and by now relatively well understood. And the typical result one can expect here is that you have two volumes. There exist two volumes, m0 less or equal m1. Below the small volume, this wins, and you are exactly a ball, which is not so immediate because the fact that this wins automatically means that you are approaching a ball for the volume going to 0, but in fact, below a certain threshold, this requires some more careful estimate, of course, isoperimetric type. If m is less than m0, then the minimizer is a ball. The minimizer is a ball of volume m. And if m is greater than m1, then the minimizer does not exist. What does it mean that the minimizer does not exist? Which means that, in fact, the minimizer in some sense exists, but it's just done by a finite number of components, which, since we have space, they just go to infinity. So it is not connected. So if it's not connected, it does not exist just because we are working on an infinite domain. If not, it exists, of course. So there is a sort of dichotomy. And I think, as I said, okay, one can have this result with more general kernels. I don't think one can get it in this generality, but okay, there are some conditions on the kernel. What is not clear here is if there is a gap between these two behaviors. So either you have a ball and then you just split, or at some point you have some minimizer, which I don't know, it's different from the ball. So it's not clear in particular here if m0 equal to m1. And I think that is an interesting question concerning this problem here. OK, so maybe just a couple of other remarks before passing to. Always concerning this functional, there is a way to eliminate the volume constraint by taking an energy which is which is unconstrained, and another problem which is of some interest. It's for example, if you just divide by the volume E here, and you don't put any constraint, that's not so. This problem comes out. Is not like totally out of the blue, but it comes out from some asymptotic regime of this problem here, when you suitably put some epsilon. So you want sort of to look of minimizers of this guy in a sort of low density regime. You scale things, and the shape of the little droplets which appear somehow are minimizers of this guy here. And it's not so easy, but it's relatively standard with the usual sort of so non-vanishing result here to show existence. It's not immediate, but this guy, in fact, so a minimizer exists. So the question here, if it's a minimizer of this guy which exists, this is written, for example, in a recent paper by Franke Lieb. But in any case, the approach is the one you have just to control the parts going to infinity as usual by compensated comparators. So the minimizer is a ball. It's a question here, which I think it's another interesting question about this functional here. So it's sort of related but different from the previous one. And another last remark on this type of problem, and then I pass to the two-phase case. Another remark is that, in fact, it's not really absolutely necessary to require integrability of the kernel. of course, if it's not integrable, it does not make sense, the energy. But one can take in some case, some kernels which are not in L1 lock. In this case, you are obliged to, you solve the problem by integrating on the set and outside the set, not twice on the set. And the typical kernel which one can consider here as like the RISC kernel, but with the power going up above the dimension. So it's this one here. And plus, let me put it S as usual. And this gives rise to what is called the fractional perimeter. So now the functional, I have to integrate now it becomes attractive. Now, since I'm integrating on E and on the complementary, if I put a plus, it's attractive, not repulsive anymore, because there is a change here. In any case, that's a way to introduce these fractional perimeters, which somehow they behave, and there is work also on this, particularly from the Texan school, let's say, and not only, also in Italian. And they sort of behave like that functional over there in the attractive regime. And you can also combine this with repulsive terms. There are many. For example, minimizer, volume constraint minimizer, in isoperimetric inequality holds, and volume constraint minimizer of the fractional perimeter are balls, like the analog of the proposition which I have here. But I don't want to enter these things. Okay, so let me just come to the functional we considered. In fact, that's a recent work we did, but it's not really completely finished, with Cicalese, Ponsiglione, De Luca, people more or less in Munich. At the time, well, Ponsiglione is in Rome, but if not, the other are at TUM in Munich. And we wanted to see what happens. The typical example is the following. If instead of one set, I have two sets, so it's two groups of people, two populations or groups, which attract each other. That's essentially, so I don't know, some biological model of, let me just introduce a function a little bit more general than the example I want. So the functional I want to consider is I have two parameters alpha beta. I have two groups, sets, phases, I don't know, and I minimize. Now I can have three types of interactions. One between the two sets, and if one really wants also some attractive or repulsive interaction inside each set. So I have three terms, and so the interaction between the two sets has to be attractive. Since I work in Rn, if it's repulsive, they just go their way, whatever it's the interior. So the interaction is attractive. So I have to choose a minus sign. I put a -2. I prefer just, don't ask me why. Sorry. And then I fix two volumes, M1, E2, M2. And I have an interaction between the first. So A and B will be just two parameters. And so it's E1, and it's K with the same. Of course, I could choose also three possible interaction kernels. I'm just modulating the same kernel with alpha and beta, because, in fact, I was originally interested in alpha equal beta equal 0, but in general, one can have this one also. And then I have an interaction inside the second phase, E2, K. And then I have an attractive with a factor 2, which comes out what's convenient for some computation. Don't remember now exactly this one, E1, E2, K. Okay, so what does it mean? The two populations attract each other, and maybe inside you have either attraction or repulsion. And clearly, for example, if the two populations attract each other, they want to stay sort of very close one to the other. But if for some reason in one population there is a much stronger, let's say, internal attraction, then maybe they don't want to mix too much with the other one. So clearly the shape of the minimizer will depend on the choice of these parameters here. Okay, so let me just comment something here. So just to give some example. Okay, the first example, as I said, the first example was the original motivation, which then I will come back on this example, is alpha equal beta equal 0. So the two groups, they just don't care one of the other. They just want to mix the two. So here you have only this term, and here somehow mixing is expected. One can expect mixing. And mixing means mixing of the two groups, mixing like that, expected, which means that it's not clear that this problem is really a minimizer, or maybe one has to relax it a little bit. Because a mix means that you have sort of really mixed phases. Okay, before going into this, another example, which I want to discuss, it's a case alpha equal beta equal 1. And K is, because that's a physical example, in fact, it's K is the Coulomb interaction. Let's say I write this Coulomb interaction, which means I have now two sets, one positively charged, the other one negatively charged, with fixed volume, and I see what happens. Here, nothing happens in this situation, because it's just a physical case. But the problem is that this is not difficult to see that the functional with this choice of kernel and alpha and beta is always positive. So this function is always positive, and as a consequence, it has no minimizer. So if I really have positive and negative charges and I let them go, they just would spread at some point and sometime at infinity. So no minimizer. But in fact, this problem can be studied under some extra constraint. And this is part, in fact, of a recent work, which is just briefly mentioned here by Bonaccini, Knupfer, and Matthias Röger, who is here. And one could ask a slightly different question. OK, if I let the two population electrons free, they just go away. But maybe I can just want to fix one. I have a charged body, positively charged, and I put some negative charge around and see how they will sort of arrange around the positively charged body. That's a very natural, in fact, question. And in fact, I don't write a theorem because I don't want to write slightly. But essentially, the problem becomes you don't fix the volume of E1. You fix E1. And you minimize only over the second one, for example, E2. And so what happens, if E1 is fixed, then E2 will stay around E1, sort of creating a screening part, all around the boundary of E1, until the negative, let's say, the other charge, let's say E2 is positive and E2, which is my variable, is negative, it will go all around until the volume becomes the same volume of E1, so the total charge becomes 0. So the minimizer will exist if M2 is less than or equal than M1. And will be, and then they also study some regularity property, but essentially the minimizer will be something which will go all around this set here. And if you add some extra charges, now sort you are already in a neutral situation. In some sense, the total charge is already 0, so the extra charges will just go away. So the minimizer here exists if the volumes are not too big. And that's something very natural if you have some repulsion. I will not consider here essentially the repulsive case, never. But in general, one could expect that if you have repulsion here, then in general, minimizer will exist if the repulsive part is not too big. That's a statement which I cannot make precise because we didn't work it out, but somehow that's something which one can expect for this problem. Okay, so first of all, I will now concentrate only on the attractive case. So you have only alpha and beta are less than or equal to 0. So the two populations the two groups attract each other, and also you have attraction inside. And depending on how strong the attraction inside could win with respect to the attraction between the different groups. So I will assume alpha less than or equal to 0 and beta less than or equal to 0. And first of all, as I said in the alpha equal beta equal 0 case, it's reasonable to expect a mixing of the population. So it's not clear that in general this problem has a minimizer. It's better to relax the problem. And the natural way to relax the problem by weak convergence of the characteristic functions is just taking densities between 0 and 1. And so the relaxed problem would just be the relaxed problem will just be the minimum. Now there are the minimum of alpha f1k plus beta f2k minus 2 f1 f2k, where these are now densities, and there are of course some natural conditions that each density is between 0 and 1. And also, I don't want, say, superposition of individuals. Let's say I don't want to have, and so I also had a condition on the sum less than or equal to 1. Okay, so this type of problems in general of minimizing, let's say, kernels have been studied also quite a bit recently in a slightly different setting, which is more the setting, for example, of probability measures. Now, of course, if you have probability measures, you sort of could have concentration of everything even in one point, which here is ruled out by assuming that we just minimize on bounded densities. But then you have to take it into account by adding some, I don't know, repulsive term for very short distance. So, however, there is a certain literature on this type of problems, mostly in the setting of probability measures, and also mostly in the dynamical case. So a lot of people, for example, Carrillo and this group, the Frances, many, in fact, I don't want to quote. Okay, so this one, also Sant'Ambrogio did something in this. Okay, so once the problem is relaxed, like every good relaxed problem, there is an existence result under this attractive assumption. That's not very surprising because everything attracts. Nothing wants to go far away. So there is a theorem that essentially, under this assumption on alpha, beta, and k, there exists always f1, a couple f1, f2 of minimizers. And one can show some property. Okay, so I don't give a proof, but the proof is always more or less the same, like for the isoperimetric problem. You have just to take care that there are parts not disappearing at infinity. Here, in principle, the vanishing, let's say, is possible because the energy is not strong enough. It does not blow up. But it's not convenient. It's clearly not convenient. It's possible. So how do you prove this? It's just assuming that there is some part where the density is very low, this part will contribute very little to the energy. And so essentially, if you take it out and put, I don't know, a ball somewhere, it's convenient. So you cannot have parts with density. Part like on a cube of side length 1, the density cannot go to, and once you have this bound, it's finished because it becomes a compact essentially. And then one can show a couple of properties of the minimizer, which are expected in the attractive case, that you don't leave, let's say, holes. You saturate the constraint. Saturate the constraint does not mean that f1 and f2 are characteristic functions, but that the sum of the two is 1. So you might have mixed parts, mixing somewhere, but maximal mixing. And also the support of the set is bounded. It's not convenient to have sort of tentacles or whatever. So the support of f1 plus f2 is compact. Okay, so that's not very surprising, but at least one has something to work with. So the question now is if we can sort of understand what is the shape of the minimizer, depending on alpha and beta, and maybe adding some condition on the interaction kernel k. So the question is, can we just describe how this minimizer is? Okay, some, yeah. Yeah, no, I forgot the volume constraint, in fact. There is also the volume constraint. Yes. Let's say maybe it's better to write in this way. 0, 1. Okay. Okay. So so there are a couple of comments. Maybe the first comment is that okay, one can guess immediately the shape of a minimizer in a simple case. Alpha equal beta equals 0, so just only interaction of the two groups, and same volume. So now one expects that they will mix as much as possible, which means, at least it's a natural expectation, which means that if the two volumes are the same, and alpha equal beta equals 0, so they just, one expects to have something like a ball and 1/2 and 1/2 of densities inside the ball. And that's not so easy, not so difficult, in fact, to prove that if, let's say, M1 equal M2, but I just mentioned because it's a simple simple proof, and alpha equal beta equals 0. In fact, it's true that F1 equal F2 and equal 1/2 the characteristic function of a ball of volume 2m. 2m. I put the volume here of the ball. And one way, but there is an assumption, we have, unfortunately, an assumption to prove this, which is that the assumption is that the functional is positive under an assumption that k, quite restrictive in fact, is not positive but positive definite in the sense that the functional f1 fk, this functional here, is positive for all f, which is quite restrictive assumption. It's like this behaves like a scalar product, basically, if I have f1. And so this sort of amounts to it's similar to ask that the Fourier transform of the kernel is positive. And that's a little restrictive, even if it's satisfied by some natural kernels, because, you know, here we want to keep the kernel as flexible as possible for applications. So requiring something like that is already quite specific. But for example, it's satisfied by the Riesz kernel. So by the Coulomb kernel in dimension at least greater than 2 and the Riesz kernel. It's satisfied this, but in general. Okay, so if you have this, then you derive, like for the scalar products, relatively simple inequality. And you want to say, to obtain this result, that if I take the average of F1 and F2, whatever F1 and F2 are, if I take the average, then I gain in energy. So from this, what I get is, from this fact quite easily, an inequality of this form, that given F1, remember I have a minus in front, in my energy, so is always less than or equal, that the same energy, of course, here it's a double integral every time. So if you rearrange here terms, this comes out to the positivity of this guy over F1 minus F2, something like that. No? And so this means, since I have a minus, that it's more convenient energetically to have the average of the two. And so as a consequence, immediately I get that F1 is equal to F2. And of course, then it's equal to 1/2. And then the shape, it's a round shape, because then the problem reduces to the problem in the proposition up there, that the round shape in the attractive situation it's better than any other shape. So it's quite, unfortunately, under some restrictive assumption, which includes the Coulomb case, but okay, then there is another maybe, okay, then there is another consequence which holds for, so now my goal is describing all the minimizers, which I cannot do completely, but I can have some result in some regime. In particular, the description will be quite accurate in the case of Coulomb kernel, which is a very specific choice, but more general. But first of all, let me give some general result which come directly by applying the Riesz inequality to my energy. So the Riesz inequality already can fix some cases, and so there is a consequence of the Riesz inequality. The fact is, I can rewrite my energy let me give a name to this energy here, like F alpha beta of E1, E2. That's my... So I can write that, in general, it's true that F alpha beta, by rearranging terms, can be written as alpha of F alpha beta of the union twice. That's just a simple minus 2, then there is an alpha plus 1, E2, E1 union E2, and then there is a plus alpha plus beta minus 2, F alpha beta of little change, little mistake. Let me put here a J. It's not correct. Where? J or E2, where with J of E, G, I just mean the double integral over E and G of my K. Okay, I'm just rearranging terms. Okay, because that's the guy to which I can apply the Ritz inequality. Okay, this guy here, I can apply the Ritz inequality to this guy. And so by Ritz inequality, you see that if all these three terms are negative, I gain by changing E2 and E1 union E2 into a ball. So directly by Ritz inequality, if I have always negative terms, I can apply Ritz inequality to all these three terms, to the characteristic functions. And so if the consequence is that if alpha is less, if alpha is in 0, 1, maybe I have to leave something out. Let's say let's say minus 1, 0. Maybe I leave it open, so at least 1 is to, and alpha plus beta minus 2. Then I have that E2 by Ritz inequality is equal to the ball of volume M2, and E1 union E2 is equal to a ball with volume M1 plus M2 and with the same center, because when I apply Ritz inequality to this, for example, to this function here, I get two balls but with the same center, because I do the Schwarz symmetrization centered in the origin both. And so this describes, so in this setting, and of course, since my initial energy is symmetric, also in the other setting, which is also 1 beta, or beta in minus 1, 0, and so this has to be true, and one of these two has to be true. Then the minimizer is, so we are in a situation of strong attraction inside one phase. We are not in the situation 0, 0. We are in a situation where we have two groups, they attract each other, but one attracts is sort of homophilia, how you say, inside, and so they want to stay together. So the effect is that the situation here is like that. The minimizer, the unique minimizer is like that. So you have E2. Now, of course, if I do one or the other, the E2 and E1 will change. Let's say in this first situation, you have E2 inside and E1 outside. I hope I didn't mix one with the two. But so you have pure phases, one inside the ball, the one who has more attraction. And all the other phase all around in an annulus. So situation is like that let's say if alpha and beta, as again, I'm looking only to the attractive case because I don't want to have problems with non-existence. But it would be interesting also to look to. So alpha and beta, I have, so situation is like that, minus 1, minus 2, minus 1, minus 2. So in these areas here, we can, well, it's easy in these two sort of things here. it's easy to solve the problem essentially by Ritz inequality directly. Here we saw it's more complicated because, for example, in the case 0, 0, and also mixing is expected, so a more complicated behavior is expected around here. And another thing which is immediate consequence of Ritz inequality is the following. What happens if the internal attraction of the two populations goes to minus? So if the two populations has a very strong internal attraction. So in the limit, when alpha and beta go both to minus infinity, however they go is not important because the fact is that at the end the relevant part is just the internal attraction. Still, they remember vaguely that there is also an attraction between the two populations. So in the limit, the shape will be just two balls because every group wants to optimize his shape. And so you have two balls by the proposition over there, and the two balls will be tangent. So in the limit here, so here you know you have this situation here. Also here, of course, with E1 and E2 exchanged. And in the limit here, you will have sort of something like that. That's only in the limit alpha and beta going to minus infinity. And that's essentially. So now what can we say a little more? OK. To say something more, now we need to do some computation. In particular, the first variation will tell us something of the functional, as usual. And so now I can tell you that I will be able to give a more complete description essentially only under the strong assumptions and K is a Coulomb interaction. So it's, but first of all, it's not difficult to compute the first variation and to get some conditions on the two phases in all this situation. So let me just maybe I cancel that one. So the first variation as always with these non-local problems, it's usually easier to work with the potential generated by the phases, and the potential generated by the phases are Vy is just Fi k. So I mean Fi k, that will be the potential generated by the phase I. And in particular, in the Coulomb case, since K is exactly the fundamental solution of the Laplace equation, this guy will just be minus, if K is Coulomb, and that's why the Coulomb case is easier, of course, because minus Laplacian of Y up to a constant is just Fi. So it will be easier to work with that. And so the first variation tells something. How do you do the first variation? Well, it's not very, for example, you exchange some individuals from one phase to another. This will respect all the constraint. Or you move outside of the support of the two phases some individual. And this will give you some inequalities from the minimality condition. And the first variation in particular gives gives something more, but I write something which is maybe significant, that a combination of the two potential, alpha plus 1 V1 minus beta plus 1 V2, on the support of the first phase is less than alpha plus 1 V1 minus beta plus 1 V2 at every point of the other phase. Particular if the two phases are mixed somewhere, so that if the two supports intersect, I will have equality in the intersection of the support, which is an information which I have to use in order to say, for example, there is mixing or there is no mixing. So equality in the intersection. Okay, so in particular, this gives me already an important information in the Coulomb case, because in the Coulomb case, okay, here I just have a condition on the potential. The condition on the potential is difficult to visualize. It would be better to have a condition on the Fi. But the relation between the potential and the Fi maybe can be given in some Fourier way. So it's not immediate to see, except if you have some nice equation like this one. Because, for example, if you take now here the Laplacian of this, inside the region of mixing, you get an inequality between a certain inequality between F1 and F2. And in particular, in the Coulomb case, you get that alpha plus 1 F1 is equal beta plus 1 F2 in the mixed region, where I have equality. And this gives me immediately the value of F1 and F2. So in particular, one gets that F1 is equal beta plus 1 alpha plus beta minus plus 2, and F2 is alpha plus 1, alpha plus beta plus 2. That's a little surprising in the sense that if I am in the Coulomb situation, super specific, unfortunately, and I have only essentially 3 possible phases, because I have pure phase 1, pure phase 2, or mixed phase, but the mixed phase has specific percentages, which do not depend on anything except alpha and beta. In particular, do not depend on the volumes. In example, if alpha equal beta equals 0, from this I get F1 equal F2 equal 1/2 in the mixed situation, which is not totally obvious a priori, this fact that you don't mix. Also, yes, yeah. Yeah. Yeah, it's 2, and you get this. So what does it mean? Again, this, of course, in the Coulomb case. I have 2 populations, alpha equal beta equals 0. We said, okay, if they have the same volume, they just mix. That's very natural to expect. What about if one group is twice the other group? What do you expect? Well, one possible expectation is that they do mix, but they do mix sort of uniformly in a ball. So with different percentages. So what is saying here is that this is not possible. Either they mix half and half, or they are separated, right? And in fact, one can show here. Of course, here you can get out of this first variation other conditions on the potentials on the boundary of the 2 phases. Let me not write down this, since I am not now able to derive many useful information, but there are other conditions which can, so you don't get only conditions on the mixed phase, but you also get conditions on the boundary of the pure phases, as is natural for the first variation. So in fact, in the Coulomb case, we can characterize exactly what happens if we have mixing. And the situation, if for example the following proposition, that if alpha equal beta equals 0, which was the case I was interested in at the beginning, and unfortunately here I have to write k Coulomb, maybe can be generalized a little bit to some other, but k Coulomb. So that's not very physical in some sense, because it's not like electrons and protons. It's like 2 groups which attract each other, but with a Coulombic interaction. Why not? I mean, it's a possibility. So it's with a force which gives the inverse of the square of the distance. Okay. And so what we get here, in fact, it's that I just write it right away. What happens? It's still the same situation of a double ball, centered ball, but the interior part is mixed, up to saturating the smallest volume. So here you have F1 equal F2 equal 1/2, perfect mixing, and outside all the rest, the members of the group we could not mix just stay around in a pure phase, like let's say F1 equal 1 if M1 is greater or equal, for example, than M2. Okay, this is not so completely trivial, and in principle, this comes from a rearrangement inequality again, as one can imagine, but it is not an immediate consequence of Ritz inequality, and that's why we need to assume Coulomb. In this type of problems, just as a little remark, I don't do the proof, but one wants to rearrange rather the potential than the density itself. That's and this requires some little. The idea is always taking some Schwarz symmetrization, but you have to work by arranging the potential and then finding the right phase generated. So there is some technicality, but in any case, one gets this. And then, starting from this fact, in the Coulomb case, one gets essentially a complete description, which I just give I just draw like that. But this, again, is something we can do completely only in the Coulomb case, and it's a following situation. This line is not so important anymore. Let me write the line. It's -1, -2, -1, -2. It's not so important. I just write because let me recall that the only regions where we have an answer for any kernel are this here, where it's this double thing. But in the Coulomb case, in fact, inside here, it's always like that, except the percentages. So the values of F1 and F2 can depend on alpha and beta, but the situation is like that. A mixing region and outside a pure phase. So situation here is always, in all this part, centered. You have a mixed region, and then you have some pure phase around. Here, so including this triangle, where in general we don't know, but here you always have pure phases. So in fact, this is not, I could even cancel maybe this one here in the Coulomb case. And here also, from the first variation, working a little bit from the first variation, you see that here also you have only pure phases. You don't have mixing. So you mixing, you have only here. But what happens is that now the two populations attract each other much more than, and so you cannot hope to have something symmetric like that. And in fact, you go in the direction of a double bubble at minus infinity, separated bubbles, so separated circle. So here you have a situation like the two phases are, I don't know. Here we don't, we just know we have two pure phases, which I expect, depending on volume, something like that, where one phase, if I approach here, one phase will enter inside, because when I arrive here, what I see if I go and touch this line -1, I will see something like that, tangent inside, when I approach this point here. When I approach minus infinity, as we said, we always see something like that. So we know only the limit situation, but what is inside here, we expect something like double bubble case. I say double bubble, but if one wants to make an analogy with the double bubble with perimeter, the right point probably will be specifically this -2, -2. But in any case, we don't know the shape here. And as a so something like that. And of course, there is a very special point here, -1, -1. Well, -1, -1 means that the two phases attract each other exactly as they do attract the other one. So they, in fact, are only one phase. So the -1, 1, 1 is a degenerate situation where you lose the distinction between the two phases. So here here is an exceptional situation where you just get a ball, and whatever you put inside, it's irrelevant because the two phases are the same. So here you can choose any F1, F2, but that's a degenerate case, only this one here. So you have this or this situation in general. Now, as a couple of remarks, it would be interesting to understand what happens if you put a little bit of, let's say, repulsion inside one phase. But as I said, not only we don't know, but in some cases you don't even expect, if you are too far away, there is already a problem, maybe not so trivial, of existence of minimizers. You have to give some bounds. And maybe also another question, which I think could be maybe interesting to look at, is, of course, you can approximate these problems with the discrete models, which means I have n and m individuals. Then I rescale things in such a way that n and m are very big, but I do see volume, so I have to the distance, the typical distance I have to fix. So I can minimize on a discrete, at a discrete level, but I have to impose that two individuals cannot come too close. So there is a way to scale things, no? And they do converge to this. And one question could be, what is, for example, in the mixing situation, what is the optimal mixing of individuals? How do they dispose? For example, one can think they would dispose on a triangle, on some lattice. So there is a question of looking at sort of a scale of how the individuals, but this is, of course requires passing through an approximation with discrete problem. This we don't know, of course. Okay, so I will stop here. Thank you very much.